So our project, for our project, we are doing object location with the MBot Ranger. My name's Jenny.
My name is Margarita.
And I'm Karan.
Okay, so the objective of our project was to have a robot that could identify objects throughout a room as it randomly explored that room. Once it identified the object, it would make a noise and then flash its lights. And the idea behind this was to help those visually impaired locate objects with the aid of the robot. And additionally, it would also label the objects on a map. And this is so later on, the robot could give a path to the object if we ever wanted to extend on this project. And the lights and the labeling on the map are both color-coded to match the color of the object. And so this is a little ad we made. You never have to worry about finding your water bottle again, because the MBot Ranger can always find it for you.
So we assembled the MBot according to the instructions included in the kit, but because we wanted to have functionality to find an object in an open space, so we got a vision sensor. So we chose PixieCam after doing some research that can be easily trained to recognize objects. So image on the right is our assembled robot. So we created a simulation environment that looks kind of like the space where we tested the robot, with the red backpack, yellow box, orange cone, and blue cylinder objects that you can see on the right. And on the next slide, you can see the real space where we did a demo and tested the physical robot. And on the right screenshot, you can see object that PixieCam was trained to recognize and that we used in the demo. So to get the image data of the world, like we mentioned, we got the PixieCam and connected it to one of the RJ25 ports located on the MBot.
Yeah, and so for the control program, our exploration was based on an algorithm, which we'll talk about later. The object recognition in the simulation was based off the color of the objects, so that we could label the map with the corresponding color. And then once an object was located, we would have the robot beep to signify that it was found. And as we showed before, the simulation world was based off the apartment that we were testing the physical robot in. And you can see that we had to update the simulation robot to have the same capabilities as our physical robot. Here we have a camera and the LED.
So we attached an LED to the robot, and the LED can be made to flash different colors depending on the object it has detected. And it can also be made to change the duration of the light when it flashes when an object is detected.
So we use the same logic for the map generation and heat application as we did for the sim in the gazebo. So because Arduino can't run sophisticated algorithms, we have the MBot just driving and sensing, and the separate control program running on the laptop simultaneously. The control program that runs on the computer receives the sensor data from the MBot through USB-C to USB printer cable, and performs all occupancy grid heat application logic. Occupancy grid map is generated after all objects are found. So we thought it would be useful, like we said, to have a vision sensor detecting objects for those visually impaired. And out of all cameras, we decided to go with the PixieCam because of its size, detection speed, and ease of training different objects. It was a little challenging connecting the two because there aren't many tutorials available on how to connect PixieCam to MBot specifically, and not just a regular generic Arduino board. That's why we couldn't use the cable that was included in the PixieCam, so we got the RJ25 to DuPont wire and connected the cable ends of the DuPont end to the corresponding pins of the input-output board of the PixieCam. And to get the data from PixieCam in the Arduino control program, we used I2C interface. And to the right, we have a short demo that shows how PixieCam identifies objects and that it was trained to detect.
And the next interesting component we wanted to talk about was the map coloring. So for this, we had the robot use its camera to detect the color of the object, and then it would place a corresponding point on the map with its color, rather than just having one color represent all objects. We thought it would be more useful for each object to have its own color. That way it's easier to distinguish between them and makes the program more useful.
And the final interesting component we added was the LED light. So this corresponds to the same as the map color. So when an object is detected, depending on the color of the object, the corresponding LED light is flashed. And in the future video demo, you could see that the LED can be made to flash different colors depending on the object it has detected. And when the object is not in his sight, the color is turned off. In other words, diminished.
And here you can see the sim output where we have some of the objects labeled with their corresponding color. So the orange is the orange cone, the red's the red backpack, and the blue is the blue cylinder. This maroon color is this box over here. And you can see the walls mapped out, and yeah. Then next we'll talk about the academic paper we used. The paper was called Improved Backtracking Algorithm for Random Tree Exploration. What this did was create a tree that represents the exploration path that the robot should take. And so the path is determined by picking the next safe node. That's a certain amount of distance away. For our purposes, we used 5 units away. And so basically what it would do is from the node it's at, it would check all of its neighbors, see which one is safe, and so it'd pick one at random, see which one is safe, move to that, and repeat that process over and over again. And what's special about this algorithm that they call improved is that once it got to a spot where there's no more safe locations to move to, it goes directly back to a spot with locations that could still lead to more exploration. So in the example to the right, you can see that going back to the start would lead to exploring more space. And so the robot would take the shortest path there rather than backtracking its way through all of the nodes that it took to get to where it was. And so some modifications we had to make to this was the paper represented safe regions with polygons, and we represented them more with a square shape because that's kind of how our occupancy grid was laid out. So it was either just easier just to check the 8 neighbors around each node rather than creating new shapes. And additionally, we calculated the most valuable node to go back to by counting how many safe neighbors it had and how far away it was, and using this to pick the most valuable node. Oftentimes this is the start, because the start there's always a lot of places to go to. And so an expected challenge that we had was working with Gazebo from the homework. We had experience with the random crashes and delays that we would get in Gazebo, and we added a video and a few slides that shows one of the issues we had.
So we did expect that it's going to be challenging to get the angle of the robot in the world, which is necessary for heat application on the map. So we did a simple math that was estimating it for us, and the same goes for X and Y position of the robot. So using the estimate angle, we calculated the robot's position in the space. And also the fact that robots can only sense what's in front of it made it difficult to implement the wall-following techniques for exploration. For unexpected challenges, it was very challenging to have MBot robot to communicate with Mac. So after numerous attempts, we had to get a laptop and completely wipe it out and install Linux to use the stream serial header.
So the next unexpected challenge we faced was the LED plugin. There was very little documentation which is available for the LED plugin, and to make the light flash different colors depending on the object was really challenging, because LED plugin is not a standalone library. It depends on another plugin known as flashlight. So these two libraries should be made to run simultaneously, and only then you could flash a light when an object is detected or change the intensity of the light.
Another unexpected challenge that we had is robot batteries dying very quickly. So we had to charge them all the time that we need to test it. And also it was very challenging, or kind of challenging, to map the object that the camera was trained to detect. Because you can imagine that there might be a mismatch between the ultrasonic sensor and the camera. So for example, the camera might see an object like somewhere like in the corner, and it might like flash a light, but the ultrasonic sensor might hit something different than the object that the camera detected.
So here's the video of one of our unexpected challenges. Yeah, so that was always a good time when that happened.
So for the demo, we first trained PixieCam to identify the objects. Then we had MBot just like autonomously driving around and avoiding obstacles. Then it was autonomously driving around and making noises and like flashing light whenever it sees an object that it was detected to train. And then once we had that, we used occupancy grid mapping for exploration and object mapping.
Yep. And then here on this slide, you can see our demo, or like a shortened version of our demo. So I'll let this play out. And there you can just see the robot moving around, and eventually it'll find the green container. On the bottom right is our control program output. And you can see it found the red box, lit up red. And here you can see the end result map, which represents the world that the robot was driving around in. And then here on this video, you can see a short example of our simulation. It'll see the red backpack, and it'll label the map red as well. And so on the next slide, you can see our references. This is the paper that we referenced for our algorithm. And if you want more information, you can follow this GitHub link to see our project. And thank you for watching.
Thank you for watching.
Yeah, thank you for watching.